This is a lecture on electron configuration, which basically gives us an address for every electron in an atom, telling us the primary energy and approximate location of the electron. So as a reminder, electrons in atoms exist in orbitals, and an orbital is simply a region of space where an electron in an atom is most likely to be found. Electron configuration is kind of a shorthand notation that gives us the information we need about a particular electron, and that notation looks kind of like this. And the number, in this case 1, tells us the energy level, the primary energy level of an electron. And so it also corresponds to the periods on the periodic table. And let's see, the letter represents the sublevel, the type of orbital S, P, D, or F, also referred to as sublevels within the primary level. And the superscript represents the actual number of electrons that are in this particular sublevel. We're also going to learn about orbital diagrams, so make sure you can differentiate the two. Electron configuration is the shorthand notation, 1s2, 2s2, etc. Orbital diagrams are more visual symbolism, where a box represents an orbital. The arrows inside the box represent electrons. And as I've mentioned before, just kind of as a reminder, every orbital can hold a maximum of 2 electrons. And by convention, an upward pointing arrow represents an electron that is spinning in the clockwise direction, and the downward arrow represents an electron in the orbital that's spinning in the counterclockwise. All right, so there are 3 rules that must be followed when writing out electron configurations for the electrons in an atom. And the first rule is called the Aufbau principle, and that simply tells us that electrons will fill the lowest available orbital first, lowest energy available orbital. And so it's important for you to know the relative energies of the orbitals that electrons can occupy. So at some point you're going to have to memorize the order. Really, if you do enough electron configuration problems like you're supposed to, you'll automatically memorize it. So just to kind of give you a visual of the energies of the orbitals, lowest energy is on the bottom with the 1s orbital, and we actually go up, farther than 5s. So there's 6s, 7s, etc. But we're just showing a portion of it. And so when you're placing electrons around electron configuration, you start at the lowest, 1s, and you just go sequentially. Okay, 2s, next is 2p, then 3s, okay, then 3p, etc. The second rule that must be followed when you're writing out an electron configuration is the Pauli exclusion principle. And the official textbook definition is that no 2 electrons in the same atom can have the same 4 quantum numbers. Okay, every electron in an atom has its own unique location and energy, etc. And that's represented by its unique 4 quantum numbers. A simpler way to look at the Pauli exclusion principle is that if 2 electrons are in the same orbital, they must have opposite spin. Now, if you remember your quantum numbers, m sub s, which is a spin quantum number, can only have 2 values. It's either going to be plus 1/2, and that's for an upward clockwise spinning electron, or it can be minus 1/2, which represents the downward pointing arrow, counterclockwise spin. And so 2 electrons in an atom can have the same N value, the same L value, and the same ML value, but what is going to be different then are the MS value, the spin. So helium, which has 2 electrons, has atomic number 2. Its electron configuration is simply 1s2. Its orbital diagram representing that configuration, it's the 1s orbital. You draw a box for it. Has 2 electrons in it. So one spins up, one spins down, and the quantum numbers for these 2 electrons are as followed. See how they have the same N value? They're both in energy level 1. They're both in an S orbital, so L is 0. M sub L is only value allowed since L is 0. And the upward spinning electron has M sub S of plus 1/2, and the other electron M sub S of minus 1/2. All right, the third and last rule that needs to be followed when writing out electron configurations is Hund's rule. And Hund's rule tends to be a little bit tricky to grasp, and several students, or a lot of students, will mix up Hund's rule with Pauli exclusion. So heads up on that, get those straight. So Hund's rule basically says that if you are talking about equal energy orbitals, so right there, what am I talking about? Well, if you get to a sublevel that has multiple orbitals in it. So do you remember a P sublevel has 3 orbitals, a D sublevel has 5, and F sublevel has 10? Okay, these multiple orbitals within the same sublevel have equal energy, okay? And so Hund's rule applies only to these orbitals. And what it says is if you're dealing with equal energy orbitals, you must put 1 electron in each of the equal energy orbitals before you pair any of them up, okay? So for example, this is what not to do on the right-hand side. We paired electrons in these equal energy orbitals before even putting one in the third P. So that's Hund's. So just a quick summary of the 3 rules that you must keep in mind. Aufbau principle, electrons go into the lowest energy orbital first. Make sure you have memorized what the order of orbitals is. No more than 2 electrons per orbital, and if you do have 2 electrons per orbital, they must have opposite spin. I forgot to add that. Opposite spin if you have 2 electrons in the same orbital. And finally, Hund's rule. When you're putting electrons in orbitals with the same energy, put 1 electron in each of the equal energy orbitals before pairing any of them. So that means, so let's start writing some electron configurations. I've mentioned the different energy levels, 1s, 2s, 2p, 3s, etc. But they all have superscripts telling us how many electrons are in each sublevel. But first, you need to know how many electrons each sublevel can possibly hold. If it is a sublevel, an S sublevel, there is only 1 orbital. Okay, so that means an S sublevel can only hold 2 electrons. If it happens to be a P sublevel, that means that you have 3 orbitals. Every P sublevel has 3 orbitals, equal energy, and each of these 3 orbitals can hold 2 electrons. And so a P sublevel can hold up to a maximum of 6 electrons. And a D sublevel, which has 5 orbitals, can hold 5 times 2 or 10 electrons. And an F sublevel can hold 14 electrons. So here are the electron configurations of the first 5 elements. Hydrogen has only 1 electron, so 1s1, and we're done. Helium has 2. Remember, a sublevel can hold 2 electrons, so and now it becomes 1s2. Lithium has 3 electrons. So once we place 2 electrons into the 1s sublevel, it's full, and we have to move to the next energy level, which is 2s. And there's 1 electron to be put into the 2s. Now, just to kind of keep track of the electrons you've placed, add together your superscripts at any point, and that will show you how many electrons you've placed so far. Skipping down to boron, okay? 1s2, 2s2, each of those are full, and we've used 4 electrons. So the 5th electron has to go in the 2p sublevel. All right, so here are some electron configurations. If you've done this before and you think you might be able to do it, go ahead and put the video on pause and give it a shot. You will need your periodic table to complete these, and I will go through them on the next slide. Alrighty, so let's just briefly go over these. Calcium has 20 electrons, so you would look on the periodic table and you would find that calcium has an atomic number of 20, which means it has 20 protons, and all elements are neutral unless you're told otherwise, which means calcium also has 20 electrons in its neutral state. So you've got to place all 20 of those electrons. So again, you need to memorize the order of energy of the orbitals. So 1s2, 2s2, so far we've used 4 electrons. 2p6, remember the p sublevel holds 6. 3s2, 3p6, 4s2. Now count up all of the superscripts and you will see they all add up to give 20, which is good. That's what you want. All right. Iron has 26 protons and electrons, and so up and through 4s2, it's the same as calcium, but it has 6 more electrons than calcium that need to be placed. So this is kind of an odd, this is if you haven't done electron configuration a long time, just to kind of remind you, these 2 orbital sublevels seem out of order. So intuitively, you might think that it would be 3s2, 3p6, and then 3d. And 4 shouldn't come until you've done all the 3s. Well, no, turns out just because of the wonders of quantum mechanics that the 4s comes before the 3d. You'll see that again with 5s. So 5s will come before the 4d, and 6s will come before the 5d. And also notice that the primary energy level drops down by a value of 1 when you go from S to D. We can talk about that more later too. But just keep that in mind. Now with that in mind, if you haven't already tried them, I would suggest shutting off the video, turning away and seeing if you can do iodine and lead by yourself. And at least at a minimum, write down the order here of orbitals from lowest to highest and make sure you commit it to memory. All right, so we talked about electron configuration, and remember in the very beginning I said we're also going to learn how to do orbital diagrams or orbital configurations. And again, that's using the boxes to represent orbitals and arrows to represent electrons in the orbital. So if you're asked to draw an orbital configuration, I usually start by writing the electron configuration for that element first, and then kind of use the electron configuration as a guide to fill up the correct orbitals. So just make sure when you are doing orbital configurations that you're following Pauli exclusion principle, which again, if you have 2 electrons in an orbital, they must have opposite spin. And make sure you're also following Hund's rule, which says if you are in equal energy orbitals within a sublevel, make sure you put one electron in each of the equal energy orbitals before you pair any up. So let's go ahead and do a practice one. Write the orbital diagram for sulfur and determine how many unpaired electrons. And so, let's see, sulfur, yeah, I've got the electron configuration right here. Sulfur has an atomic number of 16 protons, 16 electrons. So again, I would start by writing out the electron configuration and then just start placing electrons. One up, one down in each orbital until you get to equal energy orbitals, and then one in each before you pair any up. And I've got to find a home for all 16 of those electrons. So far I've placed 2, 4, 6, 8, 10. So I've got to place 6 more electrons. So 3s, 1 up, 1, 2. I have 4 electrons left. I'm going to follow Hund's rule, put 1 in each of these 3p, and then I still have 1 left over. So there is the orbital configuration or diagram for sulfur. We will go into what I'm going to briefly introduce on this slide later, but it's such an important concept that I want to just introduce it to you. It turns out that the ending of an electron configuration, the very last part of it, determines where an element is on the periodic table. And that ends up being really, really important for chemical reactivity, which we'll get into later this semester. So I'm going to do a really easy example. Let's look at lithium. Lithium is atomic number 3, which means it has 3 electrons and 3 protons, and its electron configuration is 1s2, 2s1. So what is the ending part of the configuration for lithium? It's 2s1, okay? So that 2s1 determines where lithium is on the periodic table. So it's right here, here's lithium, but I want you to look at the ending electron configuration for all of the elements in the same column or same family as lithium. Notice how they all end in S1. So this group 1A, we often refer to it as the S1 group. Now take a look at the electron configuration, the ending part of the electron configuration for all of these elements. And you'll notice that elements in the same family or same group have the same ending of their period on the periodic table. And so just right now, store that in the back of your head, and you'll understand the importance of that more later on. So chemists will often refer to group 1A as the S1 group, group 2A as the S2 group, and or this whole 1A and 2A can be the S block, and the transition metals are the D block. Okay, so D1, D2, all the way to D10. And the intertransition metals, or lanthanides and actinides, are the F block, because all of the elements down here have electron configurations that end with an F sublevel. And to the far right, the nonmetals are referred to as the P block. So again, P1, P2, 3, 4, 5, and P6. There are some electron configurations that are odd, that are unexpected. And one of them is, and I showed you, for example, the 4s sublevel comes before the 3d, 5s comes before the 4d. All right, and also there are several elements whose electron configuration is just rather odd. So look at the bottom of the page here, and if I had asked you, for example, to write out the electron configuration of any of these four, chromium, copper, molybdenum, or palladium, this is probably what you would have drawn. Take a look, however, at their actual electron configurations on the right. What has changed in all of them? In all cases, one of the s electrons has pretty much been promoted to the adjacent d sublevel. And so instead of having 4s2 or 5s2, it's 4s1 or 5s1, and then the d sublevel has an extra electron. So these simply have to be memorized. So hold on, I'll make it easier for you though. So chromium, if you look in the periodic table, chromium and molybdenum are in the same family. They're both transition metals, and they are, let's see, I think they're 4 to the right of the beginning of the D, the transition metals. So try to find them. They're right on top of each other. But basically, all of the elements in that family will have this special electron configuration. Likewise, copper, which is 9th transition metal to the right, instead of having the 4s2 3d9 electron configuration that you might expect, it again takes one of the electrons from the s sublevel and promotes it to the d sublevel. Now the reason behind this is because half full sublevels and completely full sublevels are very stable. So notice on the expected side that 3d4, okay, is not half full or completely full. So the d sublevel has 5 orbitals. And if you have 4 electrons in it, 1, 2, 3, 4, it's not half full, it's nothing special. But then if you look at how that would change in the actual electron configuration that's found, okay, so in this case you have 5 electrons in the D. So 1, 2, 3, 4, 5. And now you have exactly half full sublevel, and that is exceptionally stable. Now in the case of copper, by promoting the s electron to the d sublevel, you have a completely full d sublevel. So those anomalies just have to be memorized, basically. All right, so the final thing we're going to mention in this PowerPoint is shorthand electron configuration. Sometimes it's called noble gas electron configuration. And basically, you start out, you identify your element in the periodic table, and then you find the previous noble gas, the noble gas before it on the periodic table. So, for example, sodium's longhand electron configuration looks like this. But if you look in the periodic table, sodium is atomic number 11. So if you look at the periodic table, atomic number 10, that is the noble gas before sodium. And so you always start your shorthand configuration with the noble gas before. You put it in brackets. In this case, it's neon. Now, neon's electron configuration is 1s2, 2s2, 2p6. So by putting neon in brackets, we have avoided having to write out this part of the electron configuration. And so all you need to do after you put the nearest noble gas in brackets is account for the electrons beyond that noble gas. And in the case of sodium, The only electron that's outside of that for neon is the 3s1. So here's the shorthand for sodium. So there's a much easier way to determine the shorthand electron configuration without writing out the entire electron configuration for the noble gas. And just a reminder, in case you have gotten rusty, this group 8A are the noble gases. So let's go back over sodium. Let's say that I asked you, write the shorthand configuration of sodium. First thing you're going to do, as always, you're going to look for the noble gas nearest and before sodium. So that's neon. We're going to put that in brackets. Now, how do you know what electrons are left over beyond neon? Well, neon is atomic number 10. Simply go to the next element and account for that electron. So what electron, let me erase that. What do we call electrons that are placed right here? Okay, well, those are the 3s1 electrons. So that tells us there's the shorthand for neon. Let me do one more. Let's do oxygen, okay? So, and let me change colors here. Okay, so the noble gas nearest before oxygen is helium. So we're going to put helium in brackets. Now, we have to account for all of the electrons after helium up to and including oxygen. So that means we need to account for lithium, beryllium, boron, carbon, nitrogen, and then oxygen. Okay? So what do we have to account for? Well, we have 2s1, 2s2. You don't have to write them separately. Just say 2s2. And then what comes next? Then we have the p sublevels. How many electrons? 1, 2, 3, 4. So we have 2p4. So there's the shorthand for oxygen. So let's see if you can do some. Let's see, we just did this, okay? So what I would recommend doing is I would recommend covering up the whole right side of this and trying some of these, see if you can come up with the shorthand electron configuration. And that's it for this lecture.